Hello, hello, welcome back to another video. Today we're going to be covering membrane phospholipid synthesis, but specifically we're going to go through phosphatidylcholine. This can apply to majority of the phospholipids in the membrane anyways, but you would just have to replace the head group at the end. But it's just because we learned the PC synthesis in my lectures, so I thought I would just cover it instead. So yeah, let's get started. So as always, we have a game plan. And so the first thing that we're going to cover is the activation of the fatty acid, because if you don't do this, then you can't really start going into the pathways. Then we're going to cover the salvage pathway and then the alternate pathway. And then finally, we're going to talk oh my gosh, a little bit about the activated methyl cycle. So yeah, let's get into it, shall we? Okay, so first thing to tackle on a game plan is the activation of fatty acids. So this is done in order to get to our final product because we can't have an if we don't have an activated fatty acid, it's not going to react because there's a lot of, like with the fatty acids, it's all long hydrocarbon chains or alkyl chains. So because of this, we need to activate it. And so we have to make it ready to react with other substrates. And when we do this, we increase the reactivity of the fatty acid by activating it. And so to do this, we just add acetyl-CoA to this. This is catalyzed by acyl-CoA synthetase, and we use a molecule of ATP. Like we expend a molecule of ATP, so right now we have a net ATP of -1. Um, and so when we do this, we take that fatty acid, we add acetyl-CoA to it, we add ATP into this reaction, catalyze it by acyl-CoA synthetase, and then we get a fatty acyl-CoA. So we're just taking out that hydroxyl group at the end of that fatty acid, and we're adding the thioester linkage with that CoA enzyme. And so yeah, that's pretty much it. So now our fatty acid is activated and ready to go into the salvage pathway. So we're going to start that next. Okay, so next up we have the salvage pathway. Don't ask me why it's called the salvage pathway. I just wrote that it basically salvages my sanity because it's easier for me to remember than the alternate pathway, which uses that whole methyl cycle thing. So I know that it has something to do with preserving nucleotides, but I don't actually know the reason why it's called salvage pathway. So I will probably put it in the description, in the caption below. Not in the caption, like the description of the video, but I'll probably put it like in a subtitle or something. But so we're going to use a molecule of glycerol 3 phosphate. So it has that phosphate group on the third carbon, and that's pretty much it. Like that's all you need to know because it's glycerol 3 phosphate. So now we're going to add in two activated fatty acids. This is done by acyl transferase. So there are two acyl transferases in this pathway that in this first step. So in the first step, we're going to convert glycerol 3 phosphate into phosphatidic acid. And so this is done by adding two activated fatty acids catalyzed by acyl transferase. The first acyl transferase that enzyme is called GPAT. The second acyl transferase is called LPAT or LPAAT. And so yeah, it'll just be catalyzed twice by the same type of enzyme, but they're kind of like bunched up together in the membrane. I'll have to put a picture in there as well. But yeah, you're just going to end up with phosphatidic acid. So you're going to keep the phosphate on the third carbon, but you're going to end up with two fatty acids on carbons 1 and 2. And so that's pretty much it. So this is why we needed to activate our fatty acid in order to react with glycerol 3 phosphate. Now, when we have the phosphatidic acid, it's going to be in the plasma membrane on the cytosolic leaflet or the cytosolic side. And so at the end of this reaction, we're going to need to flip the phospholipid from the cytosolic side into the luminal side or the luminal leaflet. So that's pretty much all you need to know for this first step is that glycerol 3 phosphate is converted into phosphatidic acid through two additions of fatty acid, both catalyzed by acyl transferase, and you end up with phosphatidic acid on the cytosolic side of the plasma membrane. Okay, so now for this last step of the salvage pathway, we're going to take phosphatidic acid and we're going to remove a phosphate group. This is catalyzed by phosphatase. I know on my board I said the phosphatase enzyme removes a phosphate group from glycerol 3 phosphate. That's wrong. It's going to be removing a phosphate group from phosphatidic acid to become DAG. So DAG is diacylglycerol. oh my gosh, that's very hard to say. Diacylglycerol is called DAG. So it's basically at the end of the third carbon, it's CH2OH. So it's a hydroxyl group instead of that phosphate group. So now we're going to have choline phosphotransferase, which transfers the choline head group, which contains as well a phosphate group, onto DAG. And so when we when we add CDP choline into this reaction, we are going to have CMP come out, and that choline head group will be transferred onto the third carbon, and we're going to end up with phosphatidylcholine, also known as PC. Just remember that the choline phosphotransferase catalyzes the transfer of the choline group onto DAG. And so now our last step is to use a flippase enzyme. There's no specific name for this flippase enzyme that I learned in my lecture. I just know it as flippase. But the phosphatidylcholine will now be flipped from the cytosolic leaflet into the luminal leaflet. And voila, that's it. That's literally it. That's the salvage pathway. Okay, so for the alternate pathway, it's actually pretty simple. We're going to use phosphatidylethylamine, so PE, and we're going to successfully methylate it 3 times. And then that nitrogen group or that amine group is going to be methylated 3 times to get phosphatidylcholine. And so this is catalyzed by methyltransferase. And when you put those 3 atomets into this reaction, you're going to end up with 3 adohase coming out, which is also known as S-adenosyl homocysteine. And that's literally the alternate pathway. It's pretty simple. It's nothing too crazy. I was freaking out about it before learning it, but it's actually not too bad. So now we're going to go into the activated methyl cycle, which is how we get the synthesis of Atomet. Okay, so to make Atomet, all we need is methionine and ATP. So what happens here is, so the methionine, the sulfur atom is going to take its 2 lone pairs of electrons and it's going to nucleophilically, I hope that's a word. It's going to perform a nucleophilic attack on ATP, displacing the 3 phosphoryl groups. So it'll attack the carbon 5, 1, 2, 3, 4, 5 of um, the ribose moiety. So basically, that ribose part, it's going to attack that, which will displace that oxygen carbon bond between the ribose moiety and the ATP or the phosphoryl group section. And so that displaces 3 phosphoryl groups and forms a bond with the adenosine moiety. So methionine, that sulfur atom, forms a bond with the ribose moiety. This reaction is catalyzed by methionine adenosyl transferase, and the product is Atomet, also known as S-adenosyl methionine or Atomet. The reason that this is super reactive and will need to basically methylate other compounds due to the fact that the sulfur becomes positively charged once it is attached to the ribose moiety, and the methyl group becomes super reactive as well as super unstable, so that's why it's quite reactive and will need to basically transfer its methyl group. And so once we get to Atomet, we can do successful methylations. So I kind of put on the diagram there that I said basically methyl transferases, so it can do basically we'll do methylations like we saw with PE, and this will kind of be the yield result. So we get adohay, which is also known as S-adenosyl homocysteine. As you can see, we are still attached to the adenosine, so that sulfur is attached to the adenosine, but we don't have that anymore, so now it's not as positively charged. That sulfur group is not positively charged anymore. So after this, to get homocysteine by itself to reproduce methionine, because the goal is kind of to reproduce methionine in order to get Atomet again, so that we can keep doing this over and over to get more membrane phospholipids, basically. You're going to add water in to remove adenosine, which is catalyzed by hydrolase. And so now you're going to end up with homocysteine. So that sulfur group is not attached to adenosine anymore. It's actually attached to a hydrogen group. And this will now undergo a synthesis reaction with methionine synthetase as the enzyme that catalyzes the reaction. This reaction actually requires vitamin B12, or I guess coenzyme B12, and the methyl group that will be transferring to methionine. So basically, we're taking that homocysteine and we're just adding that methyl group, and that hydrogen will go away and get transferred. to tetrahydrofolate. But the methyl group actually comes from nitrogen 5 methyl tetrahydrofolate. And so this step is kind of irreversible. And so once you are at N, like nitrogen 5 methyl tetrahydrofolate, you can't really go to tetrahydrofolate unless you have B12. So this is a problem if you have vitamin B12 deficiency or just a B12 deficiency in general. I'm not sure how many types of B12 there are, but I know that there's like different forms, even though they're kind of like the same thing. But basically, you do need B12 in order to get from nitrogen 5 methyl tetrahydrofolate to tetrahydrofolate, which is actually very important for a lot of other things for degradation of amino acids, such as producing urea. And yeah, that's pretty much it. So now that methyl group is going to be transferred to methionine, and yeah, it's pretty much generated. So it can do its thing again, go back with ATP to form Atomet. And that's it. Yay!